my last video, I left you with a challenge, which was to come up with a theorem that relates the number of edges in a tree and the number of vertices. And we talked about this in class 2. And here is the theorem. If you try out a few examples, it seems clear that in fact you're always going to have one less edge than there are vertices. And so in this video I want to go through a careful proof of that. And of course the proof is going to be by induction on the number of vertices. Okay. I should mention, right, that the way I've written this theorem, I've written it carefully. So I say let G be a finite undirected tree with at least one vertex. And I'll let you think about what goes wrong if I omit any of these things. So if, for example, if I omit the word finite, what could go wrong? Why might this theorem not be true anymore? Also, if I omit the part about having at least one vertex, what goes wrong? I'll let you think about that. So, proof is going to be by induction on the number of vertices V. The base case, right, is when there's one vertex, then the graph just looks like this, which is indeed a tree, and clearly it has 0 edges, and so it works, right? So, well, and I guess to be really careful, we should say the reason it has no edges is because it has to be a tree. So, if I have one vertex, I could have some edges like this, right? This is a graph with one vertex, but it's got some edges, but those are cycles, right? So since it's a tree, we know it doesn't have any cycles, so it can't look like this. So really we should say the only tree which has no cycles with one vertex is this, which has 0 edges. Okay, let's look at the inductive step. Okay, so I'm going to suppose, so let K be a number at least 1, and suppose, every finite tree with at least K, or with K vertices has K minus 1 edges. And then what we have to show is that any tree that has K plus 1 vertices has K edges, right? So we must show every tree with K plus 1 vertices has K edges. Okay. I suppose I didn't really need to put the word finite here because since it has K vertices, K is a finite number. So, okay. So I'm going to first show a wrong way to do the induction step because it's and we talked about this a little bit in class the other day, and this is a very common wrong approach. So, so this is wrong. So I say, all right, let T be a tree with K edges, K vertices, and then by the induction hypothesis, it has K minus 1 edges. Okay, and then we're going to add an edge and a vertex adjacent to any vertex vertex of T. Okay, so I've got my tree T here. Right, so this is my tree T, and I've got a bunch of edges and vertices in here, and then I say, well, let's just add one new edge and one new vertex onto my tree T. And then you would say, well, we've added one edge and one vertex. It's still connected, and it still has no cycles because it's connected because I added it, adjacent to an existing vertex. And it has no cycles because adding a new edge and a new vertex can't make any cycles if there weren't any cycles before. So this tree, the new thing is still the tree, and it has k plus 1 vertices and k edges because we added one of each. Okay. So why is this wrong? Everything that I said actually is correct. Like, if we say let T be a tree with k vertices, the induction hypothesis really does tell us it has k minus 1 edges. And it really is true that if we add a new vertex and a new edge, then I will end up with a tree that has k plus 1 vertices and k edges. That's all true. The problem is that it doesn't actually show what we wanted to show. Because we wanted to show that every tree with k plus 1 vertices has k edges. And all we did here is show that if we start with a tree with k vertices, we can construct some particular tree with k plus 1 vertices. And in particular, we don't know whether it's possible to get all the possible trees with k plus 1 vertices by starting with a tree like this and adding something to it. So really, to show a for all statement like this, right? This is a for all statement. It says for all trees with k plus 1 vertices. To show a for all statement, we have to start by saying, let's suppose we have an arbitrary tree with k plus 1 vertices and go from there. We have to be able to show that any tree we could start with, that this will be true for, not just some particular ones that we can build. Okay, so let's erase this. So let T be an arbitrary tree with k plus 1 vertices. Okay, now claim T has some vertex with degree 1. And before we prove that claim, let me talk about how we're going to use this. And actually, the wrong proof is not actually that wrong. It has some right ideas, and in particular, we're going to use a similar idea, but we're just going to kind of do it backwards. So, right, here's my tree T, and the claim is that somewhere, I should draw it like this, sticking out. Right, the claim is that somewhere there's this vertex. I can find a vertex that has degree 1. And if I can find that, then I can do kind of that previous wrong proof, but kind of in reverse, where I say, all right, if I take this vertex away and I take this edge away, what am I left with? I'm left with something that has k vertices, of course, because I deleted one. But also, the thing I'm left with must still be a tree. Why is that? Well, it still is connected because anything that was in here that had a path between them, like that path still exists. Deleting this, because I deleted a vertex with degree 1, I didn't get rid of any paths, right? There was nothing that could have, the only path that could go through here is any path that was going to this vertex itself. And so I didn't disconnect it. Also, you can't possibly create any new cycles that weren't already there by deleting an edge. So it still doesn't have any cycles, it's still connected. It's a tree, it has k vertices, therefore the induction hypothesis says it has k minus 1 edges. And therefore, my tree T, right, I deleted this edge, so in fact it had k edges to start with. Okay? So I'll just say, if so, deleting that vertex plus its edge, its adjacent edge, leaves a tree with k vertices and hence k minus 1 edges by the induction hypothesis. So T has k edges. Okay? The only thing left, of course, is we have to prove this claim. We have to prove that if we have a tree with k plus 1 vertices, that we can find a vertex with degree 1. Okay, so here's how we do it. To find a vertex of degree 1, we're going to do the following. So first, pick any vertex. And notice, since the tree has k plus 1 vertices, and k is at least 1, that means it has to have 2 or more vertices. And it's connected, because it's a tree. So if you have at least 2 vertices, and it's connected, then this vertex we picked couldn't possibly have degree 0. Because if it had degree 0, it would be all by itself, it wouldn't be connected to anything else, but there's at least 2 vertices, so the whole thing would be disconnected. So it must have, or it can't have degree 0 since T has k plus 1, which is greater than or equal to 2 vertices, and is connected. Okay, so now that we know we have a vertex and it has degree at least 1, could be 5, or who knows, we can just keep following edges. Okay, so follow an edge, we'll get to another vertex, follow an edge, get to another vertex. We just want to make sure that we never go back along an edge that we've already been on before. Okay, so keep following edges, and I'll say don't retrace your steps. Okay? And I claim that eventually, if you keep doing this, you're going to come to a vertex with degree 1. Why is that? Well, first of all, since the graph is finite, I can't keep doing this forever. And I'm never going to come back to a vertex that I've been to before because there's no cycles. Okay, so every time I keep following an edge, I'm going to get to a new vertex, and I can't keep getting to new vertices forever because they're finite. So eventually, I'm going to have to get to a vertex where I stop. And the only reason that I could stop is that I get stuck, right? That I get to a vertex with degree 1, and I can't go back along the way I came in. If I'm always at vertices of degree 2 or greater, then I'll always have a way to leave from where I came in. I don't think, actually, now that I'm not going to bother writing all of what I just said. But the argument is because it has no cycles, and because it's finite, right? This process will eventually reach a vertex of degree 1 that we can then delete to use our induction hypothesis.